Okay, so um, we're still really talking about how trustworthy um, a statistic is to estimate a parameter or to estimate for a population. And most of what we're going to do during this video is talk about biased versus unbiased estimators. So for the first thing that we're going to take a look at, I think going back to the CHIPS example is an easy way to do it. So in the example, we collected many samples of 20. I think this was 500 samples of 20, and calculated a sample proportion of red chips. So we want to know how well does this sample proportion estimate the true proportion of red chips, which was 0.5, which was half. So after taking the 500 samples, they put it into a dot plot. We could see that it's centered at 0.5, and we spoke a lot about this the last class, that theoretically it should be about there. But if we were to take all possible samples of 20 to find the mean of the sample proportions, you'd get exactly 0.5. So because of this, we're going to call our sample proportion an unbiased estimator. And let's get more into that now. So what an unbiased estimator would be. So a statistic used to estimate a parameter is an unbiased estimator if the mean of its sampling distribution is equal to the true value of the parameter being estimated. So what we're going to say is that both our sample proportion and our sample mean are going to be unbiased estimators for a population. Sorry. For a population. And the reason being is because after taking many samples, you're going to see that it's going to be very close. And so because of that, we'll call them unbiased estimators. And more specifically, they're going to be helpful to us in our when we have to examine our data. But something to realize, though, is that they would really be helpful to us only when we're dealing with something like categorical variables, something like color with the chips. With quantitative variables, though, we might be more interested in the population mean or median, a minimum, a maximum, Q1, Q3, variance, standard deviation, which means also IQR, or range, okay? So now we'll talk a little bit about range or standard deviation with our statistic. So the problem being here is that with your range, your sample range, so even though a sample mean and your sample proportion is going to be an unbiased or useful estimator, often your sample range is a biased estimator. So your sample range will usually be much higher or much lower than your population range, and so we will call that a biased estimator. Now, we're not going to necessarily define that because that's not what the most important part of it is. So what's more important, so let me just write that under here right now, but you don't have much to say about it. So what we'll say is, we'll call it our sample range. We'll say our sample range is a biased estimator. And the reason because is the sample range is often much higher or much lower than your population range. It doesn't come close like your population proportion and your population mean. So that creates a problem. However, there is a way to fix it, and that's what's more important to us right now, which is the idea of low variability. So to get a trustworthy estimate of an unknown population parameter, start by using a statistic that's an unbiased estimator. So we're talking our sample proportion or sample mean. This ensures that you won't tend to overestimate or underestimate. Unfortunately, using an unbiased estimator doesn't guarantee that the value of your statistic will be close to the actual parameter value. And so because of this, we're going to start to look at the idea that the larger samples have a clear advantage over smaller samples. They are much more likely to produce an estimate close to the true value of the parameter. So I kind of said this a little bit last class, but weren't getting so much into it. So often your unbiased samples are okay in most situations, but for them to be even better, so we want lower variability, we're going to take more samples. So if you could see, this would be the 100 chips again. So in 100 samples, look how spread out it is. All the way to point 0.22 all the way to 0.52. Look in 1,000 samples, okay? Much closer together. So now you're talking, I don't know, 0.29 to 0.44. Okay, so very much closer together. And because of this, it is kind of letting us know that the more samples, the less spread out. So it's one way to kind of fix the problem of a biased estimator. In addition to this, it's also going to make your unbiased estimators even better. So the idea of taking more samples gives you a lower variability, which is better. It's better for both your unbiased estimators, it's just backing them up even more, okay? And it is giving you much less of a range for your biased estimators. So the variability of a statistic is described by the spread of its sampling distribution. This spread is determined primarily by the size of the random sample. Larger samples give smaller spread. The spread of the sampling distribution does not depend on the size of the population, as long as the population is at least 10 times larger than the sample. So that's just your 10% condition. Okay, so this is kind of a way to demonstrate what we were just saying. So you could think of the value of the population parameter as the bullseye on a target, and the and of the sample statistic as an arrow fired at the target. So both bias and variability describe what happens when we take many shots at a target. So here would be high bias, low variability. So notice that they're all kind of close together, but you missed your target. Low bias, high variability. So they're kind of all, there we go. We're kind of all scattered here. Some pretty close to the target, but none are hitting and all of them are scattered, as opposed to high bias and high variability, kind of worst case scenario, because you're nowhere near the target and you're all spread out. But here would be your ideal situation: no bias, low variability. So you are always hitting the target. So everything's close together and hitting your target. Okay, so just a few things. So there's just one thing that I want to address. It's the idea of this bias. So and we're talking about sampling. So what I do want to address is we're talking about biased and unbiased estimators, as in our means and our standard deviations or our spreads. Okay, we're not so much talking about the type of sample. So the type of sample can very much still be biased. So there's no way to correct, it doesn't fix a biased sample. It's just why, it's just why your estimators would be biased or unbiased. So a convenient sample or a voluntary response sample, those things are still biased samples. No matter how many you take, it's still biased. So we're not talking there, we're talking about the estimators from a good or unbiased sample. We're talking about those estimators, not the actual sample in itself. So just a few things to kind of conclude here. So bias means that our aim is off and we consistently miss the bullseye in the same direction. Our sample values do not center on the population value. High variability means that repeated shots are widely scattered on the target. Repeated samples do not give very similar results. The lesson about the center and spread is clear. Given a choice of statistics to estimate an unknown parameter, choose one with no or low bias and minimum variability. So essentially, this sums it up. This last part right here sums up the entire video. Okay, whoops, that was awful. And now for a check your understanding. I'm going to kind of let you guys figure this one out yourselves, and then we'll talk about it in class. We'll go over it in class. But I think you guys could probably figure out these 3 questions. They're not too bad. You can print off the notes that I made available to you on the post right before this video. And I will see you tomorrow in class.